Everyone, welcome back to another video for the series. I'm Inoki, and today I brought a very fun and interesting problem in algebra. And yes, today I'm going to share my personal solution. So it is original. I'm going to share my original solution. And if you think I made an error or if you think my solution is not complete, please feel free to share that in the comment below. And also, it took me hours to come up with this solution that I'm going to share today, so I hope you enjoy it. So first thing that we're going to do is let x sub I be arbitrary real numbers. Prove the inequality, this one. So first thing that we're going to do is we're going to simplify our inequality here. So we're going to let s sub n equals 1 plus x sub 1 squared plus all the way until x sub n squared, where s sub 0 equals 1. I'm not sure why I cannot write today, but yes, this is what we're going to do. So, rewriting the inequality, we need to prove that x sub 1 over s sub 1 plus x sub 2 over s sub 2 plus dot 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 x sub n less than root n is to be demonstrated. I think I will just write them to be demonstrated. After looking at the square root here, I really don't like square roots, especially when it comes out in inequality. So I just got pissed and I squared them. S sub I squared, it suffices to prove. Yes, after doing this, I felt way better. Yeah. Is it? Yes. Should be. Oh. Where because if the inequality holds for the original inequality holds for yeah. So what I mean by this is, if this is true, then the original inequality is true for positive numbers. But if this is true for positive, we know that it must be true for when x sub I is negative number, because we're just making our left hand side smaller. So we just need to show that this is true. Now after looking at this, what I thought of doing this is actually quite dumb, but I tried to expand them. like this. The reason why I tried to expand them is because I had no other choice. Like I was stuck like this for a few minutes, and I thought expanding was the only hope. But then I realized that addition have commutative property, meaning we can switch the orders of x of 1 over s of 1, x of 2 over s of 2, all the way until x of 1 over s of n. So switching the order does not change the sum. So what we can do here is, let's rearrange them. A can be anything, so I'll just write them. Since addition is mutative, we can rearrange the orders of such that s of x of a over s of a it doesn't have to be z. Z is the last alphabet, so I just use z, but we are not limited to 26 terms. N can be much bigger than that, or much smaller. Wait, should I use, yeah, I think I should use different, instead of z, what should we use? Because I think if I use z, no, it's like by convention, I think we can just write it. Where a, b, this set is equal to n. So what I mean by this is we're just going to rearrange them such that this is true. And notice the word rearrange here. This is where I got my next idea. So after recognizing that we can rearrange it, I wanted to use rearrangement inequality. But then I realized that instead of using rearrangement inequality, using Chebyshev's inequality will actually lead to n here. And if you watch my previous video, I think you'll remember that Chebyshev's inequality is just the direct consequence of rearrangement inequality. So after rearranging them using Chebyshev's inequality, rearrangement s of I squared over x of I squared greater than or equal to this one. So we have I over s of I equals 1 and x of I over s of I. This is true. Holds by Chebyshev's. Wait, I forgot how to spell his name. Oh yeah. Yeah, so after that, we know that this is true by Chebyshev inequality, and I'm not sure why I'm writing. Yeah. Then, wait, we know that this is true, and therefore, it suffices to prove that I equals 1 and is less than 1, since if 1 and oh my goodness, why can't I write today? Since if so I squared less than 1, then our target here, x of I over s of I squared is less than or equal to n times and I squared over x of I squared. And because this is less than 1, this should be less than n. Just multiply n on both sides. And notice that's what we want to prove here. So it suffices to prove this one, and that's the exact same thing that we have here. So we just need to prove this, then we finish our proof. Now, to be honest, I was actually quite stuck here, but notice that. So I just want to say that I felt like a genius when I came up with this idea, but I should not think like this because I think it took me a lot to come up with the next idea, but the next idea was so brilliant that I myself was really surprised. Yes, so sorry. I just realized that this is equal to x of n squared. I mean, this is so obvious. I mean, someone who is good at mathematics, who studied for Olympiad, might think that this is just an obvious fact. So why fuss about it? But for me, it was really special. And the reason why this is useful is this. Sorry, I can't speak today. Let me try that again. The reason why this is useful here is because we can actually telescope using this recursive property. And because we have s of n and s of n minus 1 here, squared is less than, is greater than or equal to so 1 times s of I minus 1, because s of I minus 1 is always less than s of I, or equal to s of I. Therefore, continuing, x of I squared over I squared, it should be less than or equal to s of I minus s of I minus 1 over s of I times s of I minus 1. Is it right? Yeah, because this thing is greater, right? Yeah. Then here comes the next genius part. Yes, this is equal to S sub I minus 1 over, over 1 minus S sub I over 1, or 1 over S sub I. Because, yeah, just make the common denominator, we know that this is true. And I was like, oh, this actually telescopes. So we know that this is equal to 1 over S of 0 minus 1 over S of n, because all the terms should cancel, and therefore it works, I think. Let me quickly think again. Yes, and that does work. Yeah, that does work. And because we define S of 0 to be 1, this is less than 1. And we just proved it. Yay! So we just proved that this thing is less than 1. And that completes our proof. So even though I'm the one who came up with the solution, I have to say I really love this solution. I think this is just perfect and elegant. Or if you have better solution, or if you think I could enhance or ameliorate this solution by writing better, or have different ideas improving, please feel free to share it in the comment below. I think because like this is one of maybe I'll say like the greatest thing that I did in my life, I'm just like that excited about math. I want to share the kicks and some of my like stories behind this problem. So I think this was the first kick, but I think this is quite obvious. I think everyone would actually do it. And actually, in first time I did it like 1 squared plus. I actually did it like this, but I didn't find it really helpful, so I just tried this one. The second kick I think here is squaring them, but I think it's also quite obvious too, squaring, because we have square root here. And the third kick is, I think, noticing the Chebyshev's inequality. Actually, we don't have to use Chebyshev's inequality. We can just multiply both sides by 2 and use completing square to prove it, but I just wanted to use this one. And here, but I think the third kick was something that's really strong because we have n here, and that's it also appears here. And proving this, I think this one is also a powerful kick. I think noticing the recursive property, and yeah. Yeah, I think. Oh, why did I? This one. And also this one was quite powerful too, because, and actually the reason why I did this is because I was actually quite stuck here, but after, so I was stuck like this, but so that's why I tried something like this too, but then I realized that this might actually turn into this one, and this telescopes, so everything turns out to be perfect, and yeah, we proved it. So thank you so much for watching this video. I hope you enjoyed it, and tomorrow I'll come back with another very fun and interesting problem. Thank you, and see you tomorrow. Bye.